So today we're going to talk about special systems of these linear equations. We've talked about how we solve them through graphing, substitution, elimination, and now we want to talk about some situations that will come about and how we can deal with those. So the graphs you see in front of you are basically giving us a little bit of some different possibilities. So when we see our lines intersect, we only have one solution, obviously because they are linear. Once they cross each other, they will continue to travel away from each other and they'll never cross again. So if the lines were to intersect, then we would only have one solution. If I then have lines that are parallel, meaning they have the same slope, but they don't have the same y-intercept, notice they do not have any points in common. The whole idea of a system is that the solution is a solution to both of the equations. So when this happens, we would say there is no solution. In this last graph, it appears that there is one line. But in reality, this is representing two different lines that just happen to be the exact same line. And because of that, we call that infinitely many solutions, or an infinite number of solutions, meaning that they really are the exact same equation. So how do we go about seeing how this works? Well, certainly we can use our graphing ways. We can certainly use the other methods as well. So let's first do this equation, this system with graphing. So basically these are in y equals mx plus b already. So what I'm going to do is kind of create our y-axis, and again I'd like you to be using a straight edge. It's not so easy for me to do that on this one. We would have our y-axis and our x-axis. If I'm graphing the first one, we have 3x is our slope, and our first point is our y-intercept at 1. So we go up 1, 2, 3, go up 1, 2, 3, and we would get an equation that's going to look something like this for y equals 3x plus 1. Our second equation, y equals 3x minus 5, 1, 2, 3, 4, 5. Our first point is our y-intercept, but we are still going up 3 over 1, up 3 over 1. And what you should notice here is, even though I don't have a nice straight line, these would be two parallel lines traveling next to each other, and they will never intersect. And it's actually minus 5, so let's get that accurate there. Okay, notice that I labeled my equations and also have our two lines. So a couple of interesting points that you want to notice here. So same slope, meaning the rate of change is the same. So here we have 3's and 3's. Different y-intercepts, though. So we have a 1 and a negative 5. That basically says these are parallel. So even without the graph, we could have kind of noticed that. So if they are parallel, there is no intersection point. And if there's no intersection points, this has no solution. So we don't just have to graph. Obviously the graph gives us the visual of those parallel lines. So let's try using the substitution method, and you certainly could have used elimination as well, but we'll just do the substitution so we practice it. So what I'm going to do is I have both of my equations equaling y. So because they both equal y, remember what we said on the substitution method is 3x plus 1, 3x minus 5. Because they both equal equal y, what I can do is set these two equal to each other. So we get 3x plus 1 equals 3x minus 5. My first step here is to bring my x's together, so I'm going to subtract 3x from both sides, and this is where we have the problem. So 3x minus 3x cancels, leaving me 1. 3x minus 3x cancels, leaving me negative 5. Well, negative 1 is not negative 5. So what we want to remember here is when the variables disappear, meaning they've canceled out. Notice the x's canceled. And left doesn't equal the right. Meaning the 1 and the negative 5 are obviously not the same. No solution. And again, we don't want to say that the solution is 0. We don't want to say that it's 1 or negative 5. There, 1 is not negative 5, which means no matter what I would plug in, I will never get those two sides to equal. So here we have another system. So we want to look at this one. So first of all, we're going to kind of create our system. What I want to look at is I have some information for two different shapes, the rectangle and the triangle, where the information is too much to be able to create this. So write and solve. So we want to write the perimeter of the rectangle. We know perimeter means I need to add up all the sides. So the rectangular perimeter formula is 2 times the length. So we have 2x would be our length, plus 2 times the width. So we have 2 of those, and if I added those together, I get the 36. We can simplify that a little bit better to make 4x plus 8y equals 36. So there's the first one of our 2 equations. So then I want to look at the second one, the triangle. Well, we know perimeter of a triangle is, again, just add the sides. This time we're given the number is 108. Well, this time I just have to do 6x plus 6x plus 24y equals 108. And again, I can simplify a little bit better to get 12x, 24y equals 108. So there's the first part, just writing our system. 4x plus 8y equals 36, 12x plus 24y equals 108. So we're going to try the graphing method first. So we're going to graph these two. They're both in standard form, so I think what we're going to do is leave them in standard form. You're going to notice that I did put them, the x and the y axes already on, so they're ready to go. Again, we're only going to really focus on the first quadrant just because we're dealing with rectangle and triangles, which basically means the solutions we're really looking for are going to be all positives. So if I use my standard form, remember how we do this. So what I want to do on the standard form is if I make x's 0, that's basically going to cover over 4x, just simply because we would end up being 0 times 4, which is 0. Then I'm left over with 8y equals 36. So to solve for y, I just divide by 8, and I'm going to get 4.5. So that will allow me to come over here and go up 4.5. 1, 2, 3, 4, and a half. Okay, we're just going to go by ones. So then I want to look at my x-intercept. So if I go to my x-intercept, I'm going to cover over this time the y's, because when the x-intercept is y equals 0, 8y becomes 0, and then I look at 4x equals 36, divide by 4, and I get my 9. So that means I come over 9, which is right here. So I have 9, 0, and we have 0, 4.5. Okay, and then by standard form, we're okay at this point saying let's just draw the line. And there is our equation, 4x plus 8y equals 36. So then we move on to the second equation. So in our second equation, again, we start looking at, well, when x is 0, that cancels, gives me 24y equals 108. When I divide 24 into 108, I also get this number right here, which is the 4.5. So if I was to try to graph this, all of a sudden I have the same spot there, which is fine. Then I move on to the second piece. If I make my y 0, that cancels out this term, leaving me with 12x equals 108. If I divide 108 by 12, I end up with the 9 that we had over here. So again, we'll notice we have the same two x-intercepts, and if I was to try to draw this, I'm basically getting the exact same line. So basically, what that's telling me is that 12x plus 24y equals 108 is basically the same as the previous equation. So what that now is leading us to think is that we have an infinite solutions, because they're all the same. What that would lead us to think is that every single point in one is every single point in the other. So let's just see how that works on an algebraic method. So we'll use the elimination method. So if I look at the elimination method, again, the system we came up with is 4x, 8y equals 36, 12x plus 24y equals 108. So again, we have the x's lined up, the y's lined up, the constant on the other side lined up. So what I'm going to look at now is trying to figure out how do I create opposite coefficients. Well, we have a 12 and a 4, 24 and an 8, 36 and an 8. So I can certainly pick any. I'm going to go with this first one here, the 4 and the 12. And to help that one out, what I need to do is look at making the 4 become a negative 12. Now, to make the 4 negative 12, I would just multiply by negative 3 across that top one. So if I multiply 4 across the top, I get negative 12x for the first term. Negative 3 times the 8y is negative 24y's. And negative 3 times 36 is a negative 108. And so then we bring in the second one, which already has that 12x to match. And then we add. So I'm hoping what you're going to notice here is, well, when I add, I get 0, or it cancels. I get 0, or it cancels. And I get 0, or it cancels. And 0 equals 0 always. So what we want to say there is not that the answer is 0, because it's not. Although I shouldn't say that. It is actually one of the answers, but there's an infinite number of other answers. So how we want to think of this is, when our variables disappear or cancel out, and the left side equals the right side, so in this case 0, 0, we say that it is infinite solutions. Okay, again, the answer is 0 technically, but it's a lot more than 0. It's an infinite number of solutions. And what this infinite solutions is basically telling me is that no matter what we plug in, because the equations are really equivalent, every single point will be shared. So that's some of the special ones. Basically, to kind of go back and do a quick recap, you're either going to have one solution if they cross once, and that's it. You'll have no solutions if the lines are parallel, or you'll have an infinite number of solutions if basically they are the same equation. And that is some of our special systems of linear equations.